Precision bits are called significantes. 14. Note that usually the number at the end of a format's name signifies how many bits it occupies, but TF32 actually has 19 bits, not 32 bits. I believe it was named so to suggest its functional compatibility with FP32. But honestly, why it's called TF32 and not TF19 keeps me up at night. An ex-coworker at NVIDIA volunteered his conjecture that people might be skeptical of weird formats, 19-bit, so naming this format TF32 makes it look more friendly. While FP64 is still used in many computations, as of this writing, FP64 is the default format for NumPy and pandas. It's rarely used in neural networks because of its memory footprint. FP32 and FP16 are more common. Other popular floating-point formats in AI workloads include BF16, BFloat16, and TF32, TensorFloat32. BF16 was designed by Google to optimize AI performance on TPUs, and TF32 was designed by NVIDIA for GPUs. 11 numbers can also be represented as integers. Even though not yet as common as floating formats, integer representations are becoming increasingly popular. Common integer formats are int8, 8-bit integers, and int4, 4-bit integers. 12. Each float format usually has one bit to represent the number's sign, i.e., negative or positive. The rest of the bits are split between range and precision. 13. Range. The number of ranged bits determines the range of values the format can represent. More bits means a wider range. This is similar to how having more digits lets you represent a wider range of numbers. Precision. The number of precision bits determines how precisely a number can be represented. Reducing the number of precision bits makes a number less precise. For example, if you convert 10.1234 to a format that can support only 2 decimal digits, this value becomes 10.12, which is less precise than the original value. Figure 7.6 shows different floating point formats along with their range and precision bits. 14.326, Chapter 7, Fine-tuning. Figure 7.6. Different numerical formats with their range and precision. Formats with more bits are considered higher precision. Converting a number with a high-precision format into a low-precision format, e.g., from FP32 to FP16, means reducing its precision. Reducing precision can cause a value to change or result in errors. Table 7.3 shows how FP32 values can be converted into FP16, BF16, and TF32. Table 7.3. Convert from FP32 values to lower precision formats. Resultant inaccuracies are in italics. FP32, FP16, BF16, TF32 0. 012 345 67890. 012 344 350 351 56250. 0123 291 0. 0123 44360 351 56250. 123456789 1234 741 210 93750. 123 535 0. 1234 1308 593751. 234567891. 234 375 1. 234 38 1. 234 375 12. 345 6789 12. 34 375 12. 375 12. 34,375,123. 456,789 123. 4,375,123. 5 123. 4375 1234. 56789 123 5. 0 123 2. 0 1234. 0 12345. 6789 1234 4. 0 123 52. 01234 4. 0123456. 789 INF a 123,392. 0123456. 0123 4567. 89 INF 123 6990. 0123 3920. 0 of values out of bound in FP16 are rounded to infinity. Note in Table 7.3 that even though BF16 and FP16 have the same number of bits, BF16 has more bits for range and fewer bits for precision. This allows BF16 to represent large values that are out of bound for FP16. However, this also makes BF16 less precise than FP16. For example, 1234. 56,789 is 1,235. 0 in FP16, 0, 0.35% value change, but 1232. 0 in BF16, 0, 208% value change. Memory bottlenecks, 327. 15 The FP16 and BF16 confusion continued with Llama 3. 1. CX and Threads discussions, 1, 2, 3, 4, and Llama. CPP's benchmark between BF16 and FP16, Bloch's write-up, and Rashka's write-up. 16 Designing numerical formats is a fascinating discipline. Being able to create a lower precision format that doesn't compromise a system's quality can make that system much cheaper and faster, enabling new use cases. When using a model, make sure to load the model in the format it's intended for. Loading a model into the wrong numerical format can cause the model to change significantly. For example, Llama 2 had its weights set to BF16 when it came out. However, many teams loaded the model in FP16 and were subsequently frustrated to find the model's quality much worse than advertised. 15 While this misunderstanding wasted a lot of people's time, the upside is that it forced many people to learn about numerical representations. The right format for you depends on the distribution of numerical values of your workload, such as the range of values you need, how sensitive your workload is to small numerical changes, and the underlying hardware. 16 Quantization The fewer bits needed to represent a model's values, the lower the model's memory footprint will be. A 10B parameter model in a 32-bit format requires 40 GB for its weights, but the same model in a 16-bit format will require only 20 GB. Reducing precision, also known as quantization, is a cheap and extremely effective way to reduce a model's memory footprint. It's straightforward to do and generalizes over tasks and architectures. In the context of ML, low precision generally refers to any format with fewer bits than the standard FP32. Quantization versus reduced precision. Strictly speaking, it's quantization only if the target format is integer. However, in practice, quantization is used to refer to all techniques that convert values to a lower precision format. In this book, I use quantization to refer to precision reduction, to keep it consistent with the literature. 328, Chapter 7, Fine-tuning. 17 Another major contributor to the memory footprint of transformer-based models is the KV cache, which is discussed in Chapter 9. 18 The smallest possible float size that follows all IEEE principles is 4-bit. To do quantization, you need to decide what to quantize and when. What to quantize. Ideally, you want to quantize whatever is consuming most of your memory, but it also depends on what you can quantize without hurting performance too much. As discussed in Memory Math on page 322, major contributors to a model's memory footprint during inference are the model's weights and activities. 17 Weight quantization is more common than activation quantization, since weight activation tends to have a more stable impact on performance with less accuracy loss. When to quantize. Quantization can happen during training or post-training. Post-training quantization, PTQ, means quantizing a model after it's been fully trained. PTQ is by far the most common. It's also more relevant to AI application developers who don't usually train models. Inference quantization. In the early days of deep learning, it was standard to train and serve models using 32 bits with FP32. Since the late 2010s, it has become increasingly common to serve models in 16 bits and in even lower precision. For example, Detmers et al. 2022 have done excellent work quantizing LLMs into 8 bits with LLM int 8 and 4 bits with QLORA, Detmers et al. 2023. A model can also be served in mixed precision, where values are reduced in precision when possible and maintained in higher precision when necessary. To serve models on the devices, Apple, 2024, leveraged a quantization scheme that uses a mixture of 2-bit and 4-bit formats, averaging 3.5 bits per weight. Also in 2024, in anticipation of 4-bit neural networks, NVIDIA announced their new GPU architecture, Blackwell, that supports model inference in 4-bit float. Once you get to 8 bits and under, numerical representations get more tricky. You can keep parameter values as floats using one of the mini-float formats, such as FP8, 8 bits, and FP4, 4 bits. 18 more commonly, however, parameter values are converted into an integer format, such as int8 or int4. Memory bottlenecks 329. 19 The authors of the XNORNet paper spun off Snore AI, a startup that focused on model compression. In early 2020, it was acquired by Apple for a reported $200 million. Quantization is effective, but there's a limit to how far it can go. You can't have fewer than 1 bit per value, and some have attempted the 1-bit representation, e.g., Binary Connect, Corberrios et al., 2015, XNORNet, Rastegari et al., 2016, and BitNet, Wang et al., 2023. 19 In 2024, Microsoft researchers, Ma et al., declared that we're entering the era of 1-bit LLMs by introducing BitNet B1. 58, a transformer-based language model that requires only 58 bits per parameter and whose performance is comparable to 16-bit Llama 2, Tuvrin et al., 2023, up to 3.9b parameters, as shown in Table 7.4. Table 7.4. BitNet B1. 58's performance compared to that of Llama 2 16-bit on different benchmarks and at different model sizes, up to 3.9b parameters. Results from Ma et al. 2024. Model size RSA ARCC HSBQ OQPQ WGU average. Llama LLM 700M54. 723. 037. 060. 020. 268. 954. 845. 5-BitNet B1. 58 700M51. 821. 435. 158. 220. 068. 155. 244. 3 Llama LLM1. 3B56. 923. 538. 559. 121. 670. 053. 946. 2-BitNet B1. 58.1. 3B54. 924. 237. 756. 719. 668. 855. 845. For Llama LLM 3B62. 125. 643. 361. 824. 672. 158. 249. 7-BitNet B1. 58 3B61. 428. 342. 961. 526. 671. 559. 350. 2-BitNet B1. 58 3. 9B64. 228. 744. 263. 524. 273. 260. 551. 2. Reduced precision not only reduces the memory footprint but also often improves computation speed. First, it allows a larger batch size, enabling the model to process more inputs in parallel. Second, reduced precision speeds up computation, which further reduces inference latency and training time. To illustrate this, consider the addition of two numbers. If we perform the addition bit by bit, and each takes t nanoseconds, it'll take 32 t nanoseconds for 32 bits but only 16 t nanoseconds for 16 bits. However, reducing precision doesn't always reduce latency due to the added computation needed for format conversion. There are downsides to reduced precision. Each conversion often causes a small value change, and many small changes can cause a big performance change. If a value is outside the range the reduced precision format can represent, it might be converted to infinity or an arbitrary value, causing the model's quality to further degrade. How to reduce precision with minimal impact on model performance is an active area of research, pursued by model developers as well as by hardware makers and application developers. 330, Chapter 7, Fine-tuning. 20. During training, the model's weights are updated via multiple steps. Small rounding changes can compound during the training process, making it difficult for the model to achieve the desirable performance. On top of that, loss values require precise computation. Small changes in the loss value can point parameter updates in the wrong direction. Inference in lower precision has become a standard. A model is trained using a higher precision format to maximize performance, then its precision is reduced for inference. Major ML frameworks, including PyTorch, TensorFlow, and Hugging Face's transformers, offer PTQ for free with a few lines of code. Some edge devices only support quantized inference. Therefore, frameworks for on-device inference, such as TensorFlow Lite and PyTorch Mobile, also offer PTQ. Training quantization during training is not yet as common as PTQ, but it's gaining traction. There are two distinct goals for training quantization. 1. To produce a model that can perform well in low precision during inference. This is to address the challenge that a model's quality might degrade during post-training quantization. 2. To reduce training time and cost. Quantization reduces a model's memory footprint, allowing a model to be trained on cheaper hardware or allowing the train-ing of a larger model on the same hardware. Quantization also speeds up computation, which further reduces costs. A quantization technique might help achieve one or both of these goals. Quantization-aware training, QAT, aims to create a model with high quality in low precision for inference. With QAT, the model simulates low precision, e.g. 8-bit behavior during training, which allows the model to learn to produce high-quality outputs in low precision. However, QAT doesn't reduce a model's training time since its computations are still performed in high precision. QAT can even increase train-ing time due to the extra work of simulating low-precision behavior. On the other hand, training a model directly in lower precision can help with both goals. People attempted to train models in reduced precision as early as 2016, see Habera et al. 2016, and Jacob et al. 2017. Character AI, 2024, shared that they were able to train their models entirely in INT8, which helped eliminate the training/serving precision mismatch while also significantly improving training efficiency. However, training in lower precision is harder to do, as backpropagation is more sensitive to lower precision. 20. Lower precision training is often done in mixed precision, where a copy of the weights is kept in higher precision but other values, such as gradients and activations, memory bottlenecks. 331. 21. Personal anecdote. Much of my team's work at NVIDIA was on mixed precision training. See Mixed Precision Training for NLP and Speech Recognition with OpenSeq2Seq, Huyen et al., NVIDIA Developer Technical Blog, October 2018. Are kept in lower precision. 21. You can also have less sensitive weight values computed in lower precision and more sensitive weight values computed in higher precision. For example, LLM-QAT, Liu et al., 2023, quantizes weights and activations into 4 bits but keeps embeddings in 16 bits. The portions of the model that should be in lower precision can be set automatically using the automatic mixed precision (AMP) functionality offered by many ML frameworks. It's also possible to have different phases of training in different precision levels. For example, a model can be trained in higher precision but fine-tuned in lower precision. This is especially common with foundation models, where the team training a model from scratch might be an organization with sufficient compute for higher precision training. Once the model is published, developers with less compute access can fine-tune that model in lower precision. Fine-tuning techniques. I hope that the previous section has made clear why fine-tuning large-scale models is so memory-intensive. The more memory fine-tuning requires, the fewer people who can afford to do it. Techniques that reduce a model's memory footprint make fine-tuning more accessible, allowing more people to adapt models to their applications. This section focuses on memory-efficient fine-tuning techniques, which centers around parameter-efficient fine-tuning. I'll also cover model merging, an exciting but more experimental approach to create custom models. While model merging is generally not considered fine-tuning, I include it in this section because it's complementary to fine-tuning. Fine-tuning tailors one model to specific needs. Model merging combines multiple models, often fine-tuned models, for the same purpose. While combining multiple models isn't a new concept, new types of models and fine-tuning techniques have inspired many creative model merging techniques, making this section especially fun to write about. Parameter-efficient fine-tuning. In the early days of fine-tuning, models were small enough that people could fine-tune entire models. This approach is called full fine-tuning. In full fine-tuning, the number of trainable parameters is exactly the same as the number of parameters. 332, Chapter 7, Fine-tuning. 22. In partial fine-tuning, it's common to fine-tune the layers closest to the output layer because those layers are usually more task-specific, whereas earlier layers tend to capture more general features. Full fine-tuning can look similar to training. The main difference is that training starts with randomized model weights, whereas fine-tuning starts with model weights that have been previously trained. As discussed in Memory Math on page 322, the more trainable parameters there are, the more memory is needed. Consider a 7B parameter model. If you use a 16-bit format like FP16, loading the model's weights alone requires 14 GB for memory. Full fine-tuning this model with the Atom Optimizer, also in a 16-bit format, requires an additional 7B times 3 times 2 bytes equals 42 GB of memory. The total memory needed for the model's weights, gradients, and optimizer states is then 14 GB plus 42 GB equals 56 GB. 56 GB exceeds the memory capacity of most consumer GPUs, which typically come with 12 to 24 GB of memory, with higher-end GPUs offering up to 48 GB. And this memory estimation doesn't yet take into account the memory required for activations. To fit a model on a given hardware, you can either reduce the model's memory footprint or find ways to use the hardware's memory more efficiently. Techniques like quantization and PEFT help minimize the total memory footprint. Techniques that focus on making better use of hardware memory include CPU offloading. Instead of trying to fit the whole model on GPUs, you can offload the excess memory onto CPUs, as demonstrated by DeepSpeed, Risley et al., 2020. We also haven't touched on the fact that full fine-tuning, especially supervised fine-tuning and preference fine-tuning, typically requires a lot of high-quality annotated data that most people can't afford. Due to the high memory and data requirements of full fine-tuning, people started doing partial fine-tuning. In partial fine-tuning, only some of the model's parameters are updated. For example, if a model has 10 layers, you might freeze the first 9 layers and fine-tune only the last layer, 22, reducing the number of trainable parameters to 10% of full fine-tuning. While partial fine-tuning can reduce the memory footprint, it's parameter inefficient. Partial fine-tuning requires many trainable parameters to achieve performance close to that of full fine-tuning. A study by Halsby et al. 2019 shows that with Bert Large, Devlin et al. 2018, you'd need to update approximately 25% of the parameters fine-tuning techniques, 333. To achieve performance comparable to that of full fine-tuning on the GLUE benchmark, Wang et al., 2018. Figure 7.7 shows the performance curve of partial fine-tuning with different numbers of trainable parameters. Figure 7.7. The blue line shows that partial fine-tuning requires many trainable parameters to achieve a performance comparable to full fine-tuning. Image from Halsby et al. 2019. This brings up the question, how to achieve performance close to that of full fine-tuning while using significantly fewer trainable parameters? Fine-tuning techniques resulting from this quest are parameter efficient. There's no clear threshold that a fine-tuning method has to pass to be considered parameter efficient. However, in general, a technique is considered parameter efficient if it can achieve performance close to that of full fine-tuning while using several orders of magnitude fewer trainable parameters. The idea of PEFT, parameter-efficient fine-tuning, was introduced by Halsby et al. 2019. The authors showed that by inserting additional parameters into the model in the right places, you can achieve strong fine-tuning performance using a small number BR of trainable parameters. They inserted 2 adapter modules into each transformer block of a BERT model, as shown in Figure 7.8. 334, Chapter 7, Fine-Tuning. Figure 7.8. By inserting 2 adapter modules into each transformer layer for a BERT model and updating only the adapters, Halsby et al. 2019, were able to achieve strong fine-tuning performance using a small number of trainable parameters. During fine-tuning, they kept the model's original parameters unchanged and only updated the adapters. The number of trainable parameters is the number of parameters in the adapters. On the GLUE benchmark, they achieved a performance within 0.4% of full fine-tuning using only 3% of the number of trainable parameters. The orange line in Figure 7.7 shows the performance delta between full fine-tuning and fine-tuning using different adapter sizes. However, the downside of this approach is that it increases the inference latency of the fine-tuned model. The adapters introduce additional layers, which add more computational steps to the forward pass, slowing inference. PEFT enables fine-tuning on more affordable hardware, making it accessible to many more developers. PEFT methods are generally not only parameter efficient but also sample efficient. While full fine-tuning may need tens of thousands to millions of examples to achieve notable quality improvements, some PEFT methods can deliver strong performance with just a few thousand examples. Given PEFT's obvious appeal, PEFT techniques are being rapidly developed. The next section will give an overview of these techniques before diving deeper into the most common PEFT technique, LoRa. Fine-tuning techniques, 335. PEFT techniques. The existing prolific world of PEFT generally falls into 2 buckets, adapter-based methods and soft prompt-based methods. However, it's likely that newer buckets will be introduced in the future. Adapter-based methods refer to all methods that involve additional modules to the model weights, such as the one developed by Halsby et al. 2019. Because adapter-based methods involve adding parameters, they are also called additive methods. As of this writing, LoRa, Hu et al. 2021, is by far the most popular adapter-based method, and it will be the topic of the following section. Other adapter-based methods include BitFit, Zakin et al. 2021, which came out around the same time LoRa did. Newer adapter methods include IA3, Liu et al. 2022, whose efficient mixed-task batching strategy makes it particularly attractive for multitask fine-tuning. It's been shown to outperform LoRa and even full fine-tuning in some cases. LongLoRa, Chen et al. 2023, is a LoRa variant that incorporates attention modification techniques to expand context length. If adapter-based methods add trainable parameters to the model's architecture, soft prompt-based methods modify how the model processes the input by introducing special trainable tokens. These additional tokens are fed into the model alongside the input tokens. They are called soft prompts because, like the inputs, hard prompts, soft prompts also guide the model's behaviors. However, soft prompts differ from hard prompts in 2 ways. Hard prompts are human-readable. They typically contain discrete tokens such as I, write, A, and lot. In contrast, soft prompts are continuous vectors, resembling embedding vectors, and are not human-readable. Hard prompts are static and not trainable, whereas soft prompts can be optimized through backpropagation during the tuning process, allowing them to be adjusted for specific tasks. 336, Chapter 7, Fine-Tuning. 23. I've never met a single person who could explain to me, on the spot, the differences between these techniques. Some people describe soft prompting as a crossover between prompt engineering and fine-tuning. Figure 7.9 visualizes how you can use soft prompts together with hard prompts to guide a model's behaviors. Figure 7.9. Hard prompts and soft prompts can be combined to change a model's behaviors. Soft prompt tuning as a subfield is characterized by a series of similar-sounding techniques that can be confusing, such as prefix tuning, Li and Liang, 2021, p-tuning, Liu et al., 2021, and prompt tuning, Lester et al., 2021. 23. They differ mainly on the locations where the soft prompts are inserted. For example, prefix tuning prepends soft prompt tokens to the input at every transformer layer, whereas prompt tuning prepends soft prompt tokens to only the embedded input. If you want to use any of them, many PEFT frameworks will implement them out of the box for you. To get a sense of what PEFT methods are being used, I analyzed over 1,000 open issues on the GitHub repository Hugging Face/PEFT in October 2024. The assumption is that if someone uses a technique, they are more likely to report issues or ask case tie-ins about it. Figure 7.10 shows the result. For p-tuning, I searched for keywords p_tuning and p-tuning to account for different spellings. Fine-tuning techniques, 337. Figure 7.10. The number of issues corresponding to different fine-tuning techniques from the GitHub repository Hugging Face/PEFT. This is a proxy to estimate the popularity of each technique. From this analysis, it's clear that LoRa dominates. Soft prompts are less common, but there seems to be growing interest from those who want more customization than what is afforded by prompt engineering but who don't want to invest in fine-tuning. Because of LoRa's popularity, the next section focuses on how LoRa works and how it solves the challenge posed by early adapter-based methods. Even if you don't use LoRa, this deep dive should provide a framework for you to explore other fine-tuning methods. LoRa, unlike the original adapter method by Halsby et al. 2019, LoRa, low-rank adaptation, Hu et al., 2021, incorporates additional parameters in a way that doesn't incur extra inference latency. Instead of introducing additional layers to the base model, LoRa uses modules that can be merged back to the original layers. 338, Chapter 7, Fine-Tuning. You can apply LoRa to individual weight matrices. Given a weight matrix, LoRa decomposes this matrix into the product of two smaller matrices, then updates these two smaller matrices before merging them back to the original matrix. Consider the weight matrix W of the dimension n times m. LoRa works as follows. 1. First, choose the dimension of the smaller matrices. Let R be the chosen value. Construct two matrices, A, dimension n times R, and B, dimension R times m. Their product is WAB, which is of the same dimension as W. R is the LoRa rank. 2. Add WAB to the original weight matrix W to create a new weight matrix W. Use W in place of W as part of the model. You can use a hyperparameter to determine how much WAB should contribute to the new matrix, W equals W plus alpha or WAB3. During fine-tuning, update only the parameters in A and B. W is kept intact. Figure 7.11 visualizes this process. Figure 7.11. To apply LoRa to a weight matrix W, decompose it into the product of two matrices A and B. During fine-tuning, only A and B are updated. W is kept intact. Fine-tuning techniques, 339. LoRa, low-rank adaptation, is built on the concept of low-rank factorization, a long-standing dimensionality reduction technique. The key idea is that you can factorize a large matrix into a product of two smaller matrices to reduce the number of parameters, which, in turn, reduces both the computation and memory requirements. For example, a 9 by 9 matrix can be factorized into the product of two matrices of dimensions 9 by 1 and 1 by 9. The original matrix has 81 parameters, but the two product matrices have only 18 parameters combined. The number of columns in the first factorized matrix and the number BR of columns in the second factorized matrix correspond to the rank of the factorization. The original matrix is full rank, while the two smaller matrices represent a low-rank approximation. While factorization can significantly reduce the number of parameters, it's lossy because it only approximates the original matrix. The higher the rank, the more information from the original matrix the factorization can preserve. Like the original adapter method, LoRa is parameter efficient and sample efficient. The factorization enables LoRa to use even fewer trainable parameters. The LoRa paper showed that, for GPT-3, LoRa achieves comparable or better performance with full fine-tuning on several tasks while using only 4.7 trainable parameters, 0.0027% of full fine-tuning. Why does LoRa work? Parameter-efficient methods like LoRa have become so popular that many people take them for granted. But why is parameter efficiency possible at all? If a model requires a lot of parameters to learn certain behaviors during pre-training, shouldn't it also require a lot of parameters to change its behaviors during fine-tuning? The same question can be raised for data. If a model requires a lot of data to learn a behavior, shouldn't it also require a lot of data to meaningfully change this behavior? How is it possible that you need millions or billions of examples to pre-train a model, but only a few hundreds or thousands of examples to fine-tune it? Many papers have argued that while LLMs have many parameters, they have very low intrinsic dimensions. Seeley et al. 2018, Agajanian et al. 2020, and Hu et al. 2021, they showed that pre-training implicitly minimizes the model's intrinsic dimension. Surprisingly, larger models tend to have lower intrinsic dimensions after pre-training. This suggests that pre-training acts as a compression framework for downstream tasks. In other words, the better trained an LLM is, the easier it is to fine-tune the model using a small number of trainable parameters and a small amount of data. 340, Chapter 7, Fine-Tuning. You might wonder, if low-rank factorization works so well, why don't we use LoRa for pre-training as well? Instead of pre-training a large model and applying low-rank factorization only during fine-tuning, could we factorize a model from the start for pre-training? Low-rank pre-training can significantly reduce the model's number of parameters, significantly reducing the model's pre-training time and cost. Throughout the 2010s, many people tried training low-rank neural networks, exemplified in studies such as low-rank matrix factorization for deep neural network training with high-dimensional output targets, Sinoth et al. 2013, Semi-orthogonal low-rank matrix factorization for deep neural networks, Pavi et al. 2018, and speeding up convolutional neural networks with low-rank expand science, Jaderberg et al. 2014. Low-rank factorization has proven to be effective at smaller scales. For example, by applying various factorization strategies, including replacing 3 by 3 convolution with 1 by 1 convolution, SqueezeNet, Iandola et al. 2016, achieves AlexNet level accuracy on ImageNet using 50 times fewer parameters. More recent attempts to train low-rank LLMs include ReloRA, Lyalin et al. 2023, and Galore, Zhao et al. 2024. ReloRA works for transformer-based models of up to 1.3b parameters. Galore achieves performance comparable to that of a full-rank model at 1b parameters and promising performance at 7b parameters. It's possible that one day not too far in the future, researchers will develop a way to scale up low-rank pre-training to hundreds of billions of parameters. However, if Agajanian et al.'s argument is correct, that pre-training implicitly compresses a model's intrinsic dimension, full-rank pre-training is still necessary to sufficiently reduce the model's intrinsic dimension to a point where low-rank factorization can work. It would be interesting to study exactly how much full-rank training is necessary before it's possible to switch to low-rank training. LoRa configurations. To apply LoRa, you need to decide what weight matrices to apply LoRa to and the rank of each factorization. This section will discuss the con-side rations for each of these decisions. LoRa can be applied to each individual weight matrix. The efficiency of LoRa, therefore, depends not only on what matrices LoRa is applied to but also on the model's architecture, as different architectures have different weight matrices. Fine-tuning techniques 341. 24. To effectively use LoRa for a model, it's necessary to understand that model's architecture. Chapter 2 already covered the weight composition of some transformer-based models. For the exact weight composition of a model, refer to its paper. While there have been examples of LoRa with other architectures, such as convolutional neural networks, Det et al., 2023, Zhong et al., 2024, Elim et al., 2024, LoRa has been primarily used for transformer models. 24. LoRa is most commonly applied to the four weight matrices in the attention modules, the query, WQ, key, WK, value, WV, and output projection, WO, matrices. Typically, LoRa is applied uniformly to all matrices of the same type within a model. For example, applying LoRa to the query matrix means applying LoRa to all query matrices in the model. Naively, you can apply LoRa to all these attention matrices. However, often, you're constrained by your hardware's memory and can accommodate only a fixed number of trainable parameters. Given a fixed budget of trainable parameters, what matrices should you apply LoRa to maximize performance? When fine-tuning GPT-3175B, Hu et al. 2021, set their trainable parameter budget at 18M, which is 0.1% of the model's total number of parameters. This budget allows them to apply LoRa to the following: 1 matrix with the rank of 8.2. 2 matrices with the rank of 4.3. All 4 matrices with the rank of 2. GPT-3175B has 96 transformer layers with a model dimension of 12,288. Applying LoRa with rank equals 2 to all 4 matrices would yield open parenthesis 12,288 times 2 times 2 close parenthesis times 4 is equal to 196,608 trainable parameters per layer, or 18,874,368 trainable parameters for the whole model. They found that applying LoRa to all 4 matrices with rank equals 2 yields the best performance on the wiki-SQL, Zhong et al., 2017, and multi-NLI, multi-genre natural language inference, benchmarks, Williams et al., 2017. Table 7.5 shows their results. However, the authors suggested that if you can choose only 2 attention matrices, the query and value matrices generally yield the best results. 342, Chapter 7, Fine-tuning. 25. As of this writing, some fine-tuning frameworks like Fireworks only allow a maximum LoRa rank of 32. However, this constraint is unlikely due to performance and more likely due to their hardware's memory constraint. Table 7.5. LoRa performance with the budget of 18M trainable parameters. Results from LoRa, Hu et al., 2021. Number of trainable parameters equals 18M weight type WQ WK WV WO WQ WK WQ WV WQ WK WV WO rank are 8888442 wiki-SQL, plus or minus 0.5%. 70, 470, 073, 073, 271, 473, 773, 7 multi-NLI, plus or minus 0.1%. 91, 090, 891, 091, 391, 391, 391. 7 empirical observations suggest that applying LoRa to more weight matrices, include ing the feed-forward matrices, yields better results. For example, Databricks showed that the biggest performance boost they got was from applying LoRa to all feed-forward layers, Suriyaraki, 2023. Fomenko et al. 2024, noted that feed-forward-based LoRa can be complementary to attention-based LoRa, though attention-based LoRa typically offers greater efficacy within memory constraints. The beauty of LoRa is that while its performance depends on its rank, studies have shown that a small r, such as between 4 and 64, is usually sufficient for many use cases. A smaller R means fewer LoRa parameters, which translates to a lower memory footprint. The LoRa authors observed that, to their surprise, increasing the value of R doesn't increase fine-tuning performance. This observation is consistent with Databricks' report that increasing R beyond a certain value may not yield any discernible increase in quality of model output. Suriyaraki, 2023. 25. Some argue that a higher R might even hurt as it can lead to overfitting. However, in some cases, a higher rank might be necessary. Rashka, 2023, found that R equals 256 achieved the best performance on his tasks. Another LoRa hyperparameter you can configure is the value alpha that determines how much the product WAB should contribute to the new matrix during merging. W equals W plus alpha or WAB. In practice, I've often seen chosen so that the ratio alpha, R is typically between 1 to 8 and 8 to 1, but the optimal ratio varies. For example, if R is small, you might want alpha to be larger, and if R is large, you might want alpha to be smaller. Experimentation is needed to determine the best R, alpha, combination for your use case. Serving LoRa adapters. LoRa not only lets you fine-tune models using less memory and data, but it also simplifies serving multiple models due to its modularity. To understand this benefit, let's examine how to serve a LoRa fine-tuned model. Fine-tuning techniques, 343. In general, there are two ways to serve a LoRa fine-tuned model. 1. Merge the LoRa weights A and B into the original model to create the new matrix W prior to serving the fine-tuned model. Since no extra computation is done during inference, no extra latency is added. 2. Keep W, A, and B separate during serving. The process of merging A and B back to W happens during inference, which adds extra latency. The first option is generally better if you have only one LoRa model to serve, whereas the second is generally better for multi-LoRa serving multiple LoRa models that share the same base model. Figure 7:12 visualizes multi-LoRa serving if you keep the LoRa adapters separate. Figure 7:12. Keeping LoRa adapters separate allows reuse of the same full-rank matrix W in multi-LoRa serving. For multi-LoRa serving, while option 2 adds latency overhead, it significantly reduces the storage needed. Consider the scenario in which you fine-tune a model for each of your customers using LoRa. With 100 customers, you end up with 100 fine-tuned models, all sharing the same base model. With option 1, you have to store 100 full-rank matrices W. With option 2, you only have to store one full-rank matrix W, and 100 sets of smaller matrices, A, B. To put this in perspective, let's say that the original matrix W is of the dimension 4096 by 4096, 16, 8M parameters. If the LoRa's rank is 8, the number of parameters in A and B is 4096 times 8 times 2 equals 65,536. In option 1, 100 full-rank matrices W totals 16. 8M times 100 is equal to 1. 68 B parameters. In option 2, one full-rank matrix W and 100 sets of small matrices, A, B, totals 16. 8M plus 65,536 times 100 is equal to 23. 3M parameters. Option 2 also makes it faster to switch between tasks. Let's say you currently serve ing customer X using this customer's model. To switch to serving customer Y, instead of loading this customer's full weight matrix, you only need to load Y's LoRa 344, Chapter 7, Fine-Tuning. 26. Search for these adapters by tags adapter, PEFT, or LoRa adapter, which can significantly reduce the loading time. While keeping A and B separate incurs additional latency, there are optimization techniques to minimize the added latency. The book's GitHub repository contains a walkthrough of how to do so. Multi-LoRa serving makes it easy to combine multiple specialized models. Instead of having one big powerful model for multiple tasks, you can have one LoRa adapter for each task. For example, Apple used multiple LoRa adapters to adapt the same 3B parameter base model to different iPhone features, 2024. They utilized quantization techniques to further reduce the memory footprint of this base model and adapters, allowing the serving of all of them on device. The modularity of LoRa adapters means that LoRa adapters can be shared and reused,